Oh, got it. Right, it's getting ready to go live. And I'll keep an eye if people are dripping in. Oh, got it. Right, it's getting ready to go live. Got it. Oh, that's not supposed to happen. All right, so I'm here. Welcome everybody to the EHV Innovation Café. Very happy to see you all online. For those who have not been here before, it's a weekly network event at the Kazerne, or organized by the Kazerne, where we want to show what Eindhoven has to offer on the fields of tech, design, and knowledge. Today we have Jet, Niek, and Leander talking about from Team Polar, talking about their zero emission pioneering in Antarctica. Yeah, looking forward to what you are going to present. Over to you.
Yeah. All right. Thank you very much. Firstly, is this hearable? Can everyone hear this? I assume that's a yes. So yeah, thank you for allowing us. We always are very enthusiastic when it comes to opportunities like this. So yeah, we're Team Polar. Yeah. Oh, how do I go back? Oh, you can scroll back. Perfect. All right. So quickly about us, we're a student team from the TUE. We founded in 2019, and we started with only 6 students. So at this point, we're already at 17 students, and we are recruiting for more for the next semester. So in the top picture, you can see the entire team. We've grown quite a bit over the past year. And as a team, we're indeed affiliated with research in Antarctica. So this is us. This is Leander, Niek, and I'm Jet. And we'll be presenting each about our own parts in the team, so to say. So since Antarctica, of course, isn't really a continent you would just go to on vacation, for instance, let's start with a couple of facts to get everyone warmed up a little. So even though it's quite small, it looks quite small on maps, it's actually quite big. It's 1.3 times the size of Europe. And similar to other continents, it's filled with mountains and volcanoes and even under ice lakes. Yeah, so these mountains, you can hardly see them because they're filled with ice and snow, which can reach up to 4 kilometers in depth, which has been frozen for over 35 million years, which is a very long time. So yeah, the South Pole holds a lot of information about the history of the Earth, but also about the present, and could potentially be devastating in the future if we keep heating the Earth the way we are doing now. So Leander will talk a bit more about how it's going at this point.
Yeah, so well, currently in Antarctica, the research that's being done is done mainly using kerosene-powered trucks. And given that they are studying the effects of climate change and whatever that entails, using kerosene-powered trucks is not really the most sustainable option and is quite hypocritical. But they are kind of forced to use it because they don't really have much of an alternative. And aside from it not being sustainable, they also have a very high cost to use these trucks, not only because the price of fuel in Antarctica is quite high, they also have to carry a lot of supplies and make sure the human operating the vehicle has enough to survive for the entirety of the time they are out in the truck. And that's where we looked at the problem in Antarctica and said, we want to pioneer a zero emission Antarctica. And that's what we formed the team on the basis of. And we've formed these 3 pillars to make research in Antarctica more sustainable, make it autonomous so you don't have the human element to it, and make it more affordable. And in order to achieve this, we're building a research vehicle, and we've decided to make it sustainable, electric, autonomous, and it should also be able to conduct research and enable research in Antarctica. Now, Yet and Nick will be talking about the sustainable and autonomous aspects of it, but I will go into the research that we plan on conducting with the vehicle, or plan on enabling rather, and the electric aspect of the vehicle. So firstly, it has to be a research vehicle. We have been talking to some researchers in Antarctica, and some of the research we could conduct with the vehicle is route mapping. Now, the terrain in Antarctica is very dangerous. There's a lot of crevices. And so it is quite difficult to just go out and explore the continent. You have to have a lot of sensors, and you have to be extra cautious because these crevices are quite deep. And yeah, it could be really dangerous if you do get stuck in one of those. So the vehicle we plan on having could be able to map out routes from one point to another. It could also gather weather data, and then it could also be used by glaciologists to take core samples and set up drilling stations for that. This is still in the works. We still haven't finalized what kind of research we plan on enabling, and we're still collaborating with researchers there. So we will get to that a bit later. But for now, we are currently building a smaller scale prototype of our final vehicle in order to test the other aspects of the vehicle and make sure that our solutions do function quite well. And so I will start with the electric aspect of it. We are currently using an electric dual motor setup. And the reason for a dual motor is because we want to drive two sides of the vehicle and have skid steering. This is also because skid steering makes the vehicle a lot easier to maneuver. If we do drive up and notice that there's one of the sensors picks up that there is a crevice there, it's a lot easier to rotate the wheels in opposite directions and just rotate on the spot and drive in a different direction rather than having to turn. And it also reduces the number of moving parts because you don't need an axle that's able to be steered. We're also using a single fixed gear because with the torque produced by the electric motors we have, it's fairly sufficient for our application. So we don't really need to have multiple gears or a CVT in the vehicle. And we're also using a chain drive. And this solution that we have chosen has been proven to work in other vehicles. And also for our prototype, it should be more than sufficient to drive. And now Yet we'll talk about the power supply and the solar aspect of the vehicle.
Yeah, so Leander already briefly mentioned it, but the rover should adhere to sustainability. But besides only being sustainable and not polluting, it should also contribute positively to the efficiency. It's already been mentioned, but to quickly go over it again, fuel-based rovers always have to go back to camp, and they have to put energy into heating and such, which a solar-based rover does not have to do. So it could drive almost infinitely, of course, with some limiting factors. So over the past years, we've been modeling mostly to get an idea of what the irradiance is in Antarctica to via that route contain the power output. However, we always lacked some data and some variables, which meant that we had to model the global horizontal irradiance ourselves, which always caused us to have very skewed results. And since research in Antarctica, especially on solar energy, is very little, we couldn't yet make models that were actually usable for power output. Luckily, this December, we got the awesome opportunity to send 2 of our members to Antarctica for 2 weeks to obtain or to do research to the intensity of the sun. This research was done with a pyranometer, spectrometer, and a solar test setup. So very quickly, a pyranometer is a meter that actually measures the intensity of the sun in watts per meter. But if you use two and you put them against each other, as you can see in the picture in the middle, you can also measure the albedo. Next to that, they also measured the light spectrum. This is because there are a lot of new innovations in variances of solar panels, for instance, in the amount of junctions or in the cell structures. And these light spectrums, they work better with certain solar panels, certain types of solar panels. So this information is really valuable for us to check which innovation or which technique works best with our application. Yeah, unfortunately, they just got back, so we cannot give you a sneak peek of what the data looks like because we haven't been able to actually go through it and see the results. So once we do get these results and once we can analyze them, we can put them in our models as well. And this will, in combination with, of course, variables from the battery and such, will give us a necessary power output, which will help us create a driving strategy. So some characteristics of what the solar system will look like. So in general, a limiting factor in solar cells and solar panels is the heating of the individual cells. However, in very cold conditions, such as on the South Pole, this phenomenon happens a lot less, meaning that the efficiency is actually better. Apart from this, our rover will also drive in the Arctic summer. We have Arctic winter and Arctic summer, and in the summer it's basically light 24/7, meaning that the solar panels can generate electricity 24/7, which again helps the vehicle drive almost indefinitely. So at this point, we estimate to have a 9.3 square meters area for our solar panels, which will most likely not be enough, or which will definitely not be enough to make our vehicle drive all the time, because there will also be snowstorms and such. So sometimes it'll need to stop and just charge fully, and then it'll be able to drive again. This, of course, is very dependent on the battery system as well. Like I already said before, the snow causes a very high albedo. We measured in Antarctica up to 75% average, which is very high. And this causes for a large amount of diffuse light. So a lot of light that hits the snow is reflected back. This in combination with the incredible low angle of the sun in the Arctic summer causes a lot of light to be vertically, which means that if the rover has a box-like shape, it's almost ideal in the amount of electricity it can generate. So some future challenges, some food for thought, so to say. Since we want to drive autonomously, these solar panels also need to be clean all the time. So ice will accumulate on top of the vertical panels or the horizontal panels. And this will limit or decrease the efficiency of the panels. And therefore, we will need some type of autonomous cleaning. And there are very good biodegradable vinegar solutions for this. However, there are very strict regulations on Antarctica, so you cannot leave anything behind, not even if it's biodegradable. So this will be a future challenge. Apart from this, shading could also potentially cause an issue, since there's always going to be at least two sides fully in shade, which can be solved by a smart solar system. It's been done quite a lot before. And getting batteries and solar system to work as one and have a matching voltage might also is also going to be a future challenge. So I'm going to give the floor to Nick.
Yes, thank you, Jan. Okay, so now to the autonomous driving part of our rover, and specifically I'm also going to relate it to the prototype which we're building this year. But first of all, I wanted to get a bit of a larger picture. So here you see the goal for the final vehicle of what the user should input, basically. So let's say there's a researcher, in this case on the left at the Princess Elizabeth basis, and they might, as a task for the rover, say, okay, I want you to go to Concordia station and pick up snow samples over here, do temperature measurements over here, and I only put 2 on the road right now, but of course this can be many more. And that's what they then ask the rover to do. Now the task of the autonomous system is basically to execute what the user wants, so to fully drive that route to the Concordia station. And as you can see, these distances can be enormous. In this case, it's 2,700 kilometers, because Antarctica, as mentioned previously, is a huge continent. So what are the key things to look out for then in our autonomous system? Well, there's 2 main pillars. First of all, we want to have 0 human intervention, since if, for instance, the vehicle would stall in the middle of the track I just shown, it would be very expensive to get people there to move the vehicle again or to get it reset. That's basically impossible. So there can be no human in the vehicle. Also, it needs to drive safely, and this is not in the sense that you usually hear for autonomous driving, like cars shouldn't hit pedestrians, for example, because on Antarctica there aren't that many people which we will find along the route. However, it should make sure that it drives safely in terms for the vehicle itself, that it doesn't get stuck anywhere, doesn't drive into crevices, since just like with the 0 human intervention part, it's impossible to correct the vehicle once it has made a move that is unsafe and therefore gets stuck. So to walk you through how we are doing the autonomous system for the prototype now, which again is a ATV-sized prototype, so it's on a bit smaller scale, but it will also be driving through snow. I put on the left here a researcher in a pickup truck, which is actually also a vehicle that they use now on Antarctica, and on the right our autonomous system. So basically, to simulate how somebody drives a car, we split the problem into 3 parts: perceiving, thinking, and acting. And I'm going to start with perceiving. So first of all, in order to know where to drive safely, the autonomous system will need some kind of eyes, some kind of vision of the environment. And for that, we had 3 different sensors as candidates. First of all, LiDAR, which is a type of technology that gets a very nice 3D image of the environment by sending lasers everywhere and timing the time between when the laser falls to send and when it comes back. And this laser is visible light. And using that, you can create a nice map of the environment by rotating the laser for all points around you, timing how long it took for the laser to come back. This was one option, and it actually results in a very nice resolution. Another option is using cameras, just like the cameras on your mobile phone. And the last option is radar, which is similar to LiDAR in the sense that it times when a pulse comes back. However, radar technology doesn't use visible light, and it uses radio frequency. And this is exactly why we opted for the last one. Since if you have radar, then if there's fog in front of the vehicle or a snowstorm, then radar can still see, since the radio frequencies are barely blocked by fog. However, LiDAR and camera, these are based on visible light, so they see exactly the same as a human in the car would, which is of course not ideal, since then our car essentially becomes blind when we're in a snowstorm. And the reason we do want to keep driving in a snowstorm is because otherwise, if we stand still, then a lot of snow accumulates and then we might get stuck. One issue we do have with radar is that on the picture on the right, you can see this is an environment measured by a car. You can see that all the gray dots are dots they got with LiDAR, and all the red dots are measurements from radar. So as you can see, the red dots are much sparser, since the resolution of radar is not as high as the resolution of LiDAR. Luckily, however, since we're on Antarctica, the features we are looking for, so the obstacles, are also relatively large, and therefore we don't need a very high resolution. And we are also in close contact with NXP and seeing how their cutting-edge radar technology can help us achieve the necessary resolution that we need. So those were the eyes of the vehicle. Now let's look at the brains of our vehicle, of how we're thinking. And at the moment, we have just subdivided the thinking process, so the algorithms that will be used to safely drive the rover, in different steps, and I've illustrated 3 of them here. So for instance, one of the steps is localization. So using, for instance, GPS data and also measurements of speed of the vehicle, we are always trying to keep a very good estimate of where the vehicle is on the Earth. Then another aspect of the thinking is surrounding analysis, so getting a nice measurement of what is around you. And then you also need to do some object filtering, like filtering, is this a wall of a research station that I'm seeing here? Or is this a box, or is this just snow? Those are all different components of our autonomous system. And using all of these inputs, in the end, the brain of our system will make a choice on what to do. However, as you might expect, this is a difficult process to make, and that's why I've got a picture on the right, which is our simulation environment. And in this simulation environment, we can quickly test out different solutions without breaking our rover by driving into anything. So that's what we are now heavily working on. This is not our vehicle in the simulation environment yet, because we are still working on that, on building that. But as you can see already, it is possible to get in sensor readings in simulation. And that's why we, of course, also need to build an environment in the simulation so we can drive around in there. And that is what we have already done and what I'll show you now. So here you can see 3 different environments which our simulated rover can drive around. First, the left one is like a general environment of rugged terrain. So the vehicle should find the optimal path so that it doesn't run too hard into all of the bumps. On the top right, you can see another environment, which is a hill. And for this one, the challenge is that our final brain or thinking algorithm should make sure that once it detects that hill, it drives around this, because the incline of the hill is too steep for the vehicle. So therefore, we would call it a route needs to be planned around the hill. And on the bottom right, you can see another large challenge, which is a crevice, which we also modeled. So this crevice is basically something we cannot drive through, and therefore the vehicle should detect that and steer away safely. Because if we were to drive into these crevices, which are also present on Antarctica, then it's basically end of the game. Okay, now then let's go to the last step, the acting. So as mentioned previously, we have skid steering, which is ideal, since skid steering basically means it's like a tank with tracks. So when we drive and we can no longer drive forwards because we see an obstacle, we can just turn in place and see where there is room with only sensors on the front of the vehicle. So that's great, but then still we need to send some kind of power to the motors through the motor controller. So I've got a picture here of a motor, and on the right is a motor controller. And basically our brain of the vehicle can only tell that motor controller, I want the motor to turn with this amount of power. However, we're then missing something, because if, for instance, one wheel is above the ground or it's slipping because it doesn't have good contact with the snow, then it might turn very fast for the power we give it. And we think, yeah, we're still going forwards, we're giving it more and more power. But that doesn't work, of course, since a slipping wheel, it doesn't make sense to spend a lot of power on that. So that's why we've also incorporated the feedback system. So by measuring the speed of all the axles, we can very well see whether the power we're sending to our wheels is being properly transferred to the ground, whether we're actually driving, and at what speed. So we're using magnets on the axle, and we're counting the amount of times the magnets pass by to get a very good estimate of the axle speed of the wheels, to be sure that we are actually driving it correctly. And that can then again be passed back as a feedback to the thinking system, so that it knows, okay, this is a good path since I'm driving the way that I want to. So those were the 3 different components of the autonomous system of the vehicle. So now I want to go a bit back, so out of the autonomous system, and look at the entire future of Team Polar. So as said, for now we're very busy with the prototype, so the ATV-sized vehicle. And that prototype, at the moment, we're busy with 2 parts. First of all, raising some funds still, since we're still limited by our budget in the building of the vehicle at the moment. And at the same time, we are building, for instance, simulation also with the rest of our budget on finishing the prototype. So we already built a frame, and we're also already have motors. And now at the end of the year, so the academic year, which is in summer, the plan is that this prototype is fully finished and it can drive autonomously, partly on solar power and all electric. And then we can test it in Scandinavia or Iceland to see whether it will properly navigate through snow, test it fully, write a good report of it, and reiterate on the design, verify whether the solution actually works, and make sure that we can scale this up to our final vehicles. And that's the goal in a few years, to have the final vehicle built. And the prototype will give us a lot of insight into the workings of the different subsystems and what we are still lacking and what's working very well. And then, of course, the final future of Team Polar is realizing the zero emission Antarctica, using that built final vehicle. So once the vehicle is there, and also already before that, we will be contacting research much more, making sure that the vehicle can operate according to their needs, and also very safely according to the zero emission pillars of Polar. And then we can finally reach this zero emission Antarctica. With that said, I would like to thank you all for listening to this presentation. We've come to the end, and I think it's time for the questions now.
Yes, thank you, Nick-Leander and Jet, for this great presentation. If anyone has any questions, you can just ask them in the Q&A thing and I'll read them out. I'll also check the YouTube stream in a minute. Ernst has a question. He's asking, why a four-wheeled car? Why not a sled, hovercraft, caterpillar vehicle? Why not a different number of wheels, etc.?
Well, I can answer that. We already have studied different options for that, and looking at the other types of vehicles, you have a lot more moving parts, and given the extreme climate, that creates a lot more problems, especially if the vehicle's gone further out. It's a lot harder to actually go and repair it, and if it gets stuck or breaks down, we can't really rescue the vehicle. We have to have a rescue plan, have a plane go in and airlift the vehicle out, which is very expensive and not really what we aim to do. And our vehicle is taking solutions from different off-road vehicles, taking their strengths essentially and putting them all together into this beefy Rover that's really gonna be able to work in the harsh climate of Antarctica.
Yes, and another interesting aspect, hovercraft was also mentioned, and maybe also drones, which are also options which we consider. But an interesting part of Antarctica is also that it's very windy. So basically anything aerial will get blown away quickly, since it's like a desert, a huge plain. So wind speeds can rise quickly, and therefore we do really need a design that's based on the ground.
Okay.
That answers the question.
Sorry?
I hope that answers the question.
Oh, Ernst, if you could let us know. Bayman asks, was it really needed to choose between either using visible light or radio frequency? Why not use both, just to be sure, get the best of both worlds? That's
a very good question. Yeah, of course, it's intuitive indeed to think more data in is better. However, we are limited by a few things. For instance, first of all, budget. LiDAR sensors are really expensive, and also they have moving parts, which is part of what makes them expensive. But again, moving parts on Antarctica is not exactly what we are looking for, since the laser is constantly being rotated, so then it can freeze and break. And then a last consideration is, even if a LiDAR would also be great in those aspects, then we would get more data in, which would mean a lot more processing. And the computers which do the processing, they also take power. And our power budget, as said previously, because we're driving fully on solar energy, is very limited. So we want to consume as little power as possible, and therefore using just radar or using the bare basics of what we need is better in this case, since then we can spend more power on the motors, which means we drive farther on the same sun.
All right. Ernst had a follow-up question. He did say that it did answer his question, but he's also asking, reducing the number of movable parts is also why you do not foresee a suspension. question mark, if I understood it right, that there is no suspension?
There's no suspension. We actually have been speaking to an Eastern European company, and they have these large tubeless tires that can actively inflate and deflate, and that acts as the suspension system of the vehicle. So we're talking to them about potentially using those tires on our Rover, and those tires seem to work really well. And given their size, they also make it a lot easier to navigate through the snow. So we don't really need a suspension system like a traditional vehicle with the tires do it themselves.
Okay. Okay. Jan would like to know, looking to the electronic, especially motor and controller, are they able to function in these extreme conditions?
Yeah, so we've looked at, we've spoken to a bunch of different companies, and we've really found motors and controllers that function at the low temperature ranges. Now, the insides of the vehicle will be quite sealed off, so we don't really have to worry about external factors too much. The biggest concern would be temperature for us, and we have really made sure that the motor and controllers we've chosen do suffice.
Yeah.
Yes, and we're also only driving during summer, which is also off Antarctica, because that's the only time we have light, which is also the warmer part of the year. So luckily, all the electronics only needs to survive during the winter when it's really cold, and then during summer when it's around -10, -20 degrees Celsius, then it also needs to be functional.
Okay. I was wondering, do you also get like inspiration from other rovers who've been in like similarly extreme conditions, such as like Mars, to think of another kind of extreme? Is that sort of useful information for you?
Yes, definitely. Very often, if we have shorter presentations, to keep it really short, we also start with the sentence that we're somewhat building a Mars rover for the Antarctic.
Mm-hmm.
So we're definitely looking into those kinds of vehicles. Like Leander already said, there's this Eastern European company that's building a very all-terrain kind of research vehicle that we're also cooperating with. So indeed, we definitely work together with other companies and other institutes that build vehicles that are also made for rough climates.
Okay. Hang on. I think Benjamin asked a question, but you said that Jan's question already answered it. Ernst again wants to know, some of you recently visited Antarctica aboard Commandant Charcot, if I'm pronouncing that right. What was the objective of this trip, and did you achieve it?
So we cannot, unfortunately, talk from experience since the three of us didn't go. The objective of the trip was to gather data, not necessarily to be fully correct. Of course, if you gather data, you cannot do it in 2 weeks. You need a much larger time span to get like actual really useful data. What this data does gather us is a validation. So we've tested some solar panels. We were able to test for albedo, for radiation, and comparing that to the data we already got from our models, we can kind of validate whether we're going in the right direction, which is already very important for us. On a more non-technical matter, it also gives us an experience on what it's like, because we've been researching it for 3 years. So it was really good for the team as well to have that experience and to be able to share it with others also in TUE.
Will there be any follow-up trips?
Yes, let's hope so.
Anytime soon, I mean.
We've established at least a good relation, so there's definitely potential for more. At this point, we really need to focus on indeed getting funds and having our prototype finished, so we can have something new to test and to actually showcase.
Yeah. There are still some questions in Zoom, but I also saw in YouTube there was a question. What would be the average speed and how much time would it take to travel the purposed 2,700 kilometers? Is there enough sunlight to make the waiting acceptable?
That is a very good question. And it's unfortunately also a question we cannot answer until we actually have the design of the final vehicle done. Since the work up till now is fully based on a prototype in which we have more sun because we're not on Antarctica at first, but also the final vehicle, there's a lot of question marks, like we don't know the solar power yet because that still needs to be drawn out of the research. We also don't know yet how efficient our vehicle will be because that's also still being researched and dependent on the components. What I can give are some estimates of which we've gathered until now, and that is that the final vehicle will travel at maximum 15 kilometers an hour, but could also be less for large efficiency. And for the amount of time it can drive, we currently do not have a very good estimate.
Yeah, it really depends on the battery capacity as well.
All right. Hang on. And Hans would like to know, could you enlarge on the way you cooperated with other disciplines and how integrative approach has been organized, especially from the creative point of view?
Well, if I understood the question correctly, I mean, we're always collaborating with a lot of different people with a lot of different backgrounds from different companies to really bring this vehicle together. And not only that, our team is made up of 17 students, and we're all from different faculties with different backgrounds, different specializations. So the collaboration has really been there since the beginning because we've always been multidisciplinary. And yeah, all I can say is when you have that diverse a background, the creativity just flows because people always have different ideas and approaches. So at least that's what I understood from the question, but if not, I'd be happy to.
Did that answer your question, Hans? Not quite, he says. Let's see. Are there like any, this is my interpretation of the question, but are there like any, oh, he said, I'm interested in the way it has been organized. So did you have any sort of tactics to sort of spark the creativity and the ideas in a way?
Yeah, so there's different ways we go around brainstorming. What we, for instance, sometimes did do, and is that we, together with the team, we sit together, and that then, of course, we already have multidisciplinary part. And then, for instance, in little groups, we often do that first. You yourself write down your ideas, then compare with someone else, and formulate your ideas together, and then present them to the group, so that you kind of build up the what we were presenting, and then in that way you can accumulate ideas, but also in the meanwhile, by first thinking about it yourself, you have a good grasp of the problem we're thinking of. And then after, in the other stages, you can learn from others. And at the meanwhile, what our other tactic is basically asking as much as possible to both our advisory board and external companies in their area of research. Since, for instance, we have contacted TNO to use them as a kind of soundboard to ask them a question and see what their response is, and often they have very good ideas, and then we present why we did something, and they also have their own opinions, of course. So then, using this difference, we can always learn a lot.
Yeah. All right. And Benjamin would like to know: did you get any help from the already successful solar car team from TU Eindhoven?
Yes, actually. Just before the Christmas break, we spoke to them, and they were transitioning between teams, and so they did help us out with a lot of components and stuff that would be useful for our vehicle. Aside from that, there's not much collaboration yet, but we are in contact with them, and they do help us out. But currently, we're quite on our own.
Especially for the solar sub team within Team Polar. Already at the beginning of last year, they have helped us make the foundation of our models. Of course, since they have done very similar modeling, only in a very different environment. But the foundation of our models, they've been a great help with, which is very nice.
Great. And Gert would like to know, what would be the most innovative idea if you finish the project, and who would benefit from it?
The most innovative within what our rover can facilitate, I assume. So that's a little bit into our business canvas, but since we're such a niche, we do not really target random market driven forces, so to say. So it's really researchers, governments, knowledge institutes, these kinds of institutes that are really interested for us. We also want to be the facilitators. So we want to be able to go up to researchers, have talks with them, what is interesting for them, our rover has. So it can also change. It could do soil samples for one summer and then do weather data for another, or all at the same time. It really depends on the demand that is there at that point. So we do not want to be the researchers ourselves. We really want to facilitate.
Okay, hope that answers your question, Gert. Everybody seems to be really happy with your replies. I'll check YouTube again to see. No, that one question was the only one. I think this is a good time to probably stop the live stream. If anyone feels the need to hang around and have a bit more of a chat with the team, everybody's very welcome to. I'll turn off